Today we're going to look at Kepler's laws, the first part of our Kepler's laws explain. And we are going to take a look at what makes up an ellipse, what is an ellipse, how we see it in the universe. And then also we're going to go through Kepler's first law and some math that comes with that as well. That's our plan for today. Tomorrow we're going to finish up Kepler's second law and Kepler's third law. But for now, just the first half together. So make sure you have Kepler's laws notes in Notability, just as I do here. We're going to be starting on the left-hand side here. And remember, don't forget about this stuff on the right-hand side. So there's going to be at points in the notes when I say, okay, go over to the right-hand side, answer that question. And that's what you'll need to do is fill out the stuff on this side over here. Okay? So let's get right into it. Kepler's laws explained. So we're looking at Johannes Kepler on the left-hand side here, and he has three laws of planetary motion. So a couple things to think about as we go forward. We're going to talk about these in class. What do you recall about our solar system? Have you ever made a poster or model of the solar system in our school, or in school? So thinking about kind of like how the solar system is arranged, what's at the center. It didn't always used to be that way. Up until like the 1600s, we thought that the Earth was at the center, but now we know the sun is at the center. Did you show all the planets moving in circular orbits around the sun? So in our first Explorer, you showed that, well, maybe everything's not perfectly circular. It might be really close, but it's not perfectly circular. And then finally, what characteristics can impact gravity? That's going to be a key question for us. So looking at learning target 1, parts of an elliptical orbit. Here's your first blank. Remember, this goes in the blanks on your notes, so follow along. Kepler's first law states that all objects orbit in an elliptical shape. So, for example, down here, we can see that this is an elliptical shape, not a perfect circle. And on the right-hand side, I like this one even more because it's showing the difference between a perfect circle right there to an ellipse, and showing how it's just a little bit different. It looks similar, but an ellipse is that oval shape. And in an ellipse, we have two foci. They're called not foci, but foci. Points inside an ellipse that determine the shape. So down here, it's these two X's right here. One focus is occupied by the object being orbited. So in the case of our solar system, we're talking about the sun. So one of these, this would be the sun right here. And the other one is just the other focus. In a perfect circle, there's only one focus. It's just right at the center. But if you remember those push pins that we used in Explorer 1, that shows us that there are two foci rather than just one focus. So we're just going through parts of an ellipse. We know that it's an elliptical orbit, and there's foci within that orbit. Okay, next. So distances within the ellipse help determine the various details about that object's motion. So we can see a couple different things that are labeled here. First is the major axis. So that is, let's go blue here, this line all the way across. That is the major axis. It measures the longest distance across the ellipse, crossing both foci. So notice how I hit this focus and this focus over there. And then the semi-major axis, which is shown in green up here, is just straight up half of the ellipse, straight up half of the major axis. And this only crosses through, as you can see, one focus over there. So for us in this class, you don't need to worry about this stuff up here. We are just going to be focused on the major and minor axes. The major axis is the whole thing. Semi-major axis is just literally half of it, crossing only through one foci, or one focus, I should say. Okay, moving right along. So we know we have foci, we have an elliptical shape, right? We have our two foci right here. We have an elliptical shape. It's an ellipse. We just talked about the major axis, which goes all the way across. We talked about the semi-major axis. We've used this guy in calculations a couple times. And that just goes from the absolute center to one of the sides, and that goes through one of the foci. Well, next, there's two more points we need to talk about. Because these orbits are elliptical, there's a point right over here where the planet is physically closest to the sun, and oppositely, there's a point over here that's the farthest away from the sun. And we call those points perihelion and aphelion. So perihelion is the point where the Earth or the orbiting object is closest to the sun. That's the point that's absolutely closest to the sun. And then the opposite is true when we talk about aphelion. Remember, aphelion means away. Away. Aphelion means away. That's the farthest point away from the sun. So perihelion's all the way over here, aphelion's all the way over there. Perihelion's super close. Remember, A away, aphelion away, farthest point away from the sun. Okay, on the right-hand side of your notes, there's a diagram. I want you to label those things on the diagram. So if you're watching this video right now, go ahead, hit pause, and label that diagram on the right side of your notes. This is the one we're talking about, right here. Go ahead and label the outline in yellow, put a blue dot over each foci, the major axis in green, put a semi-major axis and label it with a bracket, and then finally label perihelion and aphelion. So pause right now and go ahead and do that. Okay, as we go through labeling the outside of the ellipse in yellow, that's just this entire oval. Each of these foci gets a blue dot. The major axis is all the way across, and then the semi-major axis is just, if you can remember, just half. Let me get this guy, there we go, just half. And then we have perihelion. Over here, it's the point closest to the sun, perihelion, and aphelion would be over here, the point farthest away from the sun. All right, so talking about how we can calculate and quantify ellipses, they have a measure called eccentricity, so how elliptical these orbits are. So we can see that this red one right here is a perfect circle all the way around. And then we look at this pink one, and the pink one's actually very elliptical. So we can see how orbits can change, their eccentricity can change from very elliptical, like the pink one, which would be close to a 1, to the red one, which would be close to a 0, super circular. So eccentricity can approach 1, but eccentricity is actually never going to equal 1. As it stretches and flattens out or squashes a little bit, it'll get closer to that 1. It just will never equal a 1. But an orbit that's a perfect circle, which would be, very unlikely to find, would be very close to a 0. So kind of the same thing. Those are the ends of the spectrum, but it needs to be between this 0 and 1 number. And as it stretches out, it gets more elliptical. Its eccentricity is higher. It approaches the value of 1. Okay, on the right-hand side, you have 5 different ellipses you need to look at. You need to put all 5 of those numbers next to the ellipse or the circle that you think is best represented by those numbers. Okay, so pause the video now. Do that on the right side of your notes. Okay, so we've completed learning target 1. We've talked about the parts of an elliptical orbit. We're going to keep moving in this video, but at this point you should be able to very confidently go in and answer learning target 1. Okay, so let's talk Kepler's first law. So this is now learning target 2, looking at Kepler's first law. And Kepler's first law is really simply, it's often called the law of ellipses. So Kepler's first law is saying that, hey, all orbits are elliptical. That's straight up Johannes Kepler's first law. the orbit of a planet is an ellipse with the sun at one focus. So if you remember our diagrams from earlier, we have, I'll draw it up here, we have our ellipse, we have focus 1 and focus 2 over here, which is the sun, and that's Kepler's first law, that we have an ellipse, the orbit, it's an ellipse, we have the sun right in here, and the other focus over there. That's Kepler's first law, right there. So all planets orbiting our sun move in some sort of elliptical path, some more elliptical than others, depending on their level of eccentricity. Remember, that's the value that goes from 0 to 1. This is circular. Sorry, well, I spelled that wrong. Extra L in there. Let's try that again. Circular. There we go. That's what we're looking for. So circular for 0, and then we have elliptical over here, close to number 1. So remember, this is, I love this GIF. We've seen this before. It goes from supercircular to elliptical and kind of shows you how those orbits look different. Remember, perfect circle is 0, and as it approaches 1, it becomes more elliptical. Now, that's like the 8th time I've said that, so that's probably something that's going to be important for you to understand. Okay, so that's the concept behind it, but now we are actually able to calculate this going forward. This is what we did in our Big E Explorer. We used our small q and our large q values from sun to perihelion and sun to aphelion to calculate how elliptical or the eccentricity of the orbit. So since we know planets' distance over at aphelion and at perihelion, we can actually go through and calculate what the eccentricity is. So we're going to do this one together. So we're looking at first capital Q. So this is, well, let me back up. This is going to help us determine F, which is the distance between two foci points. So we're looking at the distance between two foci points. So essentially, we're trying to find this measurement right here, from foci to foci. That's what we're doing, because we're subtracting those, and that would make sense that we're subtracting the difference between them. So we're taking 0.61, which is our capital Q. We're subtracting 0.22. Now, if we take 0.61 and we subtract 0.22, we would expect to get 0.39. So that is our F value. That is our F value, 0.39. Okay, moving right along, we're trying to find the D value now. That's the total diameter, D diameter. So we're going to add together our lowercase q and our capital Q. And when we add them together, we get 0.83. So this is our D value. 0.83. So now we have our F value from the previous slide, which was 0.39. And we have the D value, which is 0.83. And that's all we need to calculate eccentricity. Now we know that eccentricity is F over D. So if we take 0.39, which is our F, we divide it by 0.83, which is the D value, we would get 0.470 as the eccentricity. Now, if we're remembering back to a couple slides ago, we know that 0.470, well, that's pretty much straight up in the middle between that 0 to 1 spectrum of circle to ellipse. So that would be categorized as kind of right in between a circle and an ellipse, like halfway going from a perfect circle to a perfect ellipse, so almost right in the middle. Okay, we have one more to try. And this one, I'm actually going to pause right here. And I'm going to let you do this one by yourself. So you can calculate using the Q values over here. This would be our lowercase q, because it's the distance from the sun to the perihelion, so that'd be our lowercase q. And over here would be our capital Q. It's the distance from the sun to the aphelion over there. Okay? You can calculate that one. You can handle that. When you're done, we have a summary question. Why are the distances to planets given as an average rather than an exact number? That's probably a question that you've heard talked about in class before. So you should be able to answer that at this point. Okay? That's going to conclude our first video, our day 1 video. Finish that learning target 1, finish this summary question, finish that calculation, and then reach out to your teacher if you have questions. But otherwise, we should be good to go. Thanks for watching.